Welcome to this new session of Quantum in Practice. We are starting the first session with QUOBLY because we're going to have two sessions, one today with Marta Brzezińska and next week with Alain Champenois. We're very happy to welcome you today. I will just present briefly the organizers and then I will let you with the QUOBLY experts. So deeptech Quantum Computing Initiative is one of the organizers, TQCI. Its objectives are to develop the ecosystem and prepare skills and identify use cases to improve the understanding of programming and models. To that purpose, TQCI organizes seminars throughout the year. You can find some replays in the agenda with the QR code you see on the screen. And TQCI works at consolidating the ecosystem through projects with industrial members, such as this one, Quantum in Practice. It organizes Quantum in Practice with CCFR, which is another project led by deeptech. CCFR is part of the EuroCC project and serves as the French NCC among 36 centers in Europe. The objectives are to connect industrials, academics, and public administrations with the right resources, projects, and training opportunities. It also aims at mapping key players so everyone can access the most relevant expertise in HPC, AI, and quantum computing. Our missions revolve around the various actions you see on the screen, with the constant goal of supporting you free of charge. It's always free of charge. Let me just highlight our company support, which is personalized and tailored to each need. Examples and details and interviews are available on our website and YouTube channel to give you an overview of what we can offer and how we can help in the use of HPC and quantum computing, whatever the subject is. So please don't hesitate to contact us. Let me also tell you a bit about our trainings. We organize summer schools throughout the year, and you also have access to many webinars and trainings on various topics and levels. You can find the full list on our website and connect on LinkedIn so you don't miss anything. All sessions are recorded, such as today, so you can catch up anytime on our YouTube channel. And let me just focus today on Grey Scott School 2026, which is an HPC summer school, and it's gonna start on 22nd of June, so it's soon. Registrations are still open. You can attend on-site in various countries or online. So I will give the links on the chat later, and please join us. We'll be very happy. This brings us to today's webinar. Quantum in Practice is dedicated to exploring tools and real-world applications for you to practice with today's quantum ecosystem. Each session features a leading quantum technology provider. Today is QUOBLY, next week is QUOBLY again. We have some replays with Pascal and QPerfect also, and you'll have soon some dates with AIS Plus and IBM, Quandela, IQM, and other ones. So we can start today. If you have any question, please use the chat as the Q&A, and every question will be answered at the end of the presentation. Now it's time to give the floor to Alain Champenois, who will introduce Marta Brzezińska. And thank you for listening and enjoy your webinar.
So good afternoon, everyone. I'm going to share my screen. You should be able to see my slides. I'm going to give you a few slides of introduction for QUOBLY. So I'm happy to be here. Thank you for your participation. And welcome to this first QUOBLY workshop. If you are new to this domain, welcome also to quantum computing. It's a rare deep tech technology where you can enjoy working with people who can push the boundary of science and engineering at the same time. and do it with this level of rigor and ambition. So let's start with where QUOBLY stands today. In June 2026, we began late 2022 as a bold spin-off from CEA and CNRS in Grenoble, in the French Alps. And we have quickly evolved into a deeply international force, as you can see. Today, we are a world-class team of over 100 physicians and engineers, representing 18 nationalities, and with more than half holding PhDs, quite rare as well. Our footprint now reach from Paris and Taiwan to subsidiaries in Singapore and Canada. And most importantly, we are backed by an exclusive industrial partnership with ST Microelectronics. And thanks to them, we have assembled the exact talent and ecosystem required to redefine the limits of computing. So today, I'm pretty happy to announce to you that we are writing a great new chapter of QUOBLY, and also for the entire quantum industry, backed by this 115 million euro Series A. We are moving past tech validation and stepping into an industrial execution. We are also thrilled to announce that our first quantum computer will be available on the cloud by the end of launching this year. Since we're talking in an ecosystem of HPC and cloud providers, I'm going to say a few words about how easy it is to integrate our future quantum computing platform into standard data center. And the question, of course, you are going to deep dive today about our hardware. But the main question that we are answering is that what if the secret of scaling quantum computing already existed into the global semiconductor industry? In fact, when you integrate a quantum computer into a data centers, the question that you may ask yourself is how quickly this hardware is going to be obsolete. And we have many answers that are quite interesting to that specific question. Specifically, thanks to our semiconductor qubits, we will be able to have upgrades by keeping a constant footprint of about 10 square meter on the floor level, and also with a power consumption that is controlled and that will grow smoothly with the number of qubits. And all of this is available thanks to our FDSOI technology that is protected by more than 65 patents. And this technology, in fact, allows us to manufacture at the nanoscale level both the control electronics and the qubits on the same die at cryogenic sub-Kelvin temperature. All of these characteristics makes, of course, the integration of QUOBLY's quantum computer easy into data centers and future HPC centers. So to finish, today you are very lucky because you will have the opportunity to have a great expert. Marta is going to talk about our qubits and about our hardware. She is a quantum computing hardware expert at QUOBLY. And so, Marta, the floor is yours.
Thank you very much, Alain, for this presentation and sharing the good news. Thanks a lot, Marie, for also introducing me and the company and giving this opportunity to present our work at QUOBLY. So, as always, I hope that you can see my screen. Perfect. So let me just move this and we have good to I've been working at QUOBLY since February this year, and the work that I'm going to present actually started even before that. I will talk mostly about the SpinPulse code a code which is developed at QUOBLY and is meant to faithfully simulate silicon spin qubit systems. And I believe that after this session, you will have a better understanding of why actually we would like to use the silicon spin qubits, why this is a leading platform for a scalable quantum computation, then why and how we can connect the physical concepts, physical quantities such as spins with more abstract aspects such as circuits, qubits. And in particular, I would like to focus on the QUOBLY's chosen architecture, so how we can actually do these things in the lab. And finally, I also want to put an emphasis why the existing simulators, codes which are able to simulate circuits at the gate levels are just insufficient for this hardware. So as it was announced in the abstract, my presentation will actually consist of two parts. So first of all, I will give you this short presentation to physics and code, why we do it, how we do it, and also with some set of examples that I find very interesting. Then there will be a Q&A session, so feel free to write questions anytime, but probably I will try to address them just after this presentation. I also think it would be a good idea to have like a 5 minutes break just after the QA session to grab some water, some coffee, and then we will go to the second part, that is the demo, the really hands-on presentation of the code capabilities. Okay, so quantum computing with spin qubit. Of course, when we are talking about qubits, we need to go to the basics, that is distinguish the classical systems and the quantum systems for the computation. So what we know that classical computations are based on bits. So these are either 0 or 1s, and experimentally, this is realized, for example, via transistors, that if there is like a low voltage passing by, then we have a 0, and otherwise, in terms of high voltage state, we have a qubit can be seen as an extension in the quantum realm of such a two-level system within one particular feature, that is, we not only have zeros and ones, but we actually can have a superposition or a linear combination of these two states. So, of course, not all the linear combinations are giving us qubits. What is important is that alpha and beta are complex probability amplitudes, and this is what we call the direct representation of a vector state. And because these are the complex numbers, we also ensure that these numbers are normalized to 1, meaning that the probabilities will sum. And the time evolution of such a state is deterministic. So this happens by solving the most of the time-dependent Schrödinger equation. It's a unitary evolution, meaning that it's energy preserving, it is reversible, but all this evolution happens in the Hilbert space. However, for us, for observers, of experimentalists, whatever we name it, we don't have access to quantum superposition. What we have access only to is what happens after the measurement. And this is given by the Born rule from the quantum mechanics, meaning that measuring such a system yields either a state 0 with a probability modulus alpha squared, or the state 1 with the probability modulus beta squared. So we only have access to zeros and ones, which are actually very classical. So we don't have access directly to the superposition. The superposition is destroyed because the measurement is irreversible. We only obtain the set of 0 and 1s, which we call bit strings. So by repeating the experiments on and on, getting sets of 0s and 1s, we can get an idea of what we actually getting from this evolution here. One of the nice things from the mathematical perspective is such a state can be parameterized using the block sphere representation. So each state, each single qubit state can be represented in such a sphere, and in particular we can represent all type of single qubit operations on it, such as rotations. So by definition, the north pole corresponds to the 0 state, south pole corresponds to the 1 state, and then we have two angles, so theta and phi. The theta is a polar angle which actually tells us the population or the probability of getting 0 versus 1. And then the phi is actually the azimuthal angle, which tells us about the quantum phase. It's exactly this guy. So, okay, we have like a background about the single qubit description, but the interesting things happens when we have more than one qubit. So what happens if we consider 2 and more qubit states? So the Hilbert space of such system is in fact a tensor product of local Hilbert spaces. So this leads to the scaling, to the exponential scaling with the number of qubits. So here we already see that when it comes to simulation, to really describe multi-qubit systems, we are getting very much limited because, for example, we cannot anymore store all these numbers, these amplitudes on the computer. But with multi-qubit states, there also comes a quantum resource, which is called the entanglement, meaning that by definition, we say that a state is entangled if it cannot be factored into the tensor product of individual qubit states. So in other words, we can say that the state is really non-separable. One of the examples is the Bell state. In fact, we have 4 Bell states. Here is shown just one of them. What it means is that despite having the maximal global knowledge about the state, we actually cannot say anything about individual qubit states. Like the information, it no longer lives on the individual qubits, but actually in the correlations. So when we are talking about the algorithms that's supposed to show some speed up in comparison to classical algorithms, we use entanglement as a resource. However, the problem is that when the system interacts with the environment, the entanglement can be easily destroyed, meaning that the way we process the information is no longer correct, the information is destroyed. So the question is how, from this theoretical description of qubits, we can go to a more concrete experimental realizations, especially knowing that having some unwanted couplings to environment is very much prevalent in experimental setups. So here we actually can take a look on the seminal paper of David DiVincenzo from early 2000s. He gave a pretty precise list of criteria for defining a good quantum computation platform. 5 specifically for quantum computations, there are 2 other for quantum communication, which is not relevant for today. But the point is that silicon spin qubits, by definition, they satisfy all these 5. So the remaining challenge, like why we still work on this problem, is that we really need to engineer all these steps at the scale with sufficient fidelity for fault tolerance. So just to say that, for example, DiVincenzo very clearly said that scalability and having a well-defined qubits, which are defining the computational basis, it's really the key. because, for instance, in early 2000s or even before that, there was one of the proposal based on NRM for quantum computation, and after a couple of years, we knew that it's not going to work because it's not scalable. Another thing that we can do is that we can actually initialize a state, a reference state that we use for initialization of any other algorithm later on. We can really prepare it very well, like with a very high fidelity. Why? Because, for example, we can suppress thermal fluctuations coming from the lattice. We can just cool down the system so that it stays in its ground state. And this happens in the scale of tens, hundreds millikelvins. The third thing is related to the coherence. So we don't need our qubits to be coherent all the time, infinite amount of time, but rather we want them to be coherent just that we can execute the gates. So if we prepare the gates that are very, very fast, and then we have also sufficiently long coherence times, we can really enter into this fault tolerance. Finally, the universal set of quantum gates, that means that we can actually use this platform to realize both single and 2-qubit gates, which would form a universal set of quantum gates. This I will talk in more details. And finally, of course, preparing the system is one thing, but also measuring it is very important. In these systems, we really see a very great capability based on the so-called spin-to-charge conversion, where we can really read the signal which comes from the single spin. So let me first of all introduce a little bit of math, how we can see the spin as a qubit. So the most straightforward example is to look at an isolated electron, which is a two-level system, but its energy levels are degenerate. So that means that we have two energy states with the very same energy. So first of all, what we need to do is to lift this degeneracy or split these energy levels. And this can be done by applying a static magnetic field with some value B0. And this is what we call the Zeeman effect. So just to prepare the computational basis, we need to do this. And from now on, I'm saying that we are applying this static magnetic field along the z-axis. This would be our quantization axis. So this two-level system is described by the simple 2x2 Hamiltonian, where Z is the Pauli matrix, G is the G factor, and here is Bohr magneton, which this one is a constant. And if we diagonalize this Hamiltonian, we actually have a formula for the strength of the Zeeman splitting. So we see that it's very much proportional to the magnetic field that we apply. And as I said, this is our assumption that this is the computational basis. So we normally say that the state which is lower in energy, or the ground state, this will be our zero state. And then the excited state, higher in energy, will be denoted here. So one of the things that happens when we have this magnetic field is that if the spin is not exactly parallel to B0, so when it's not pointing exactly along the z-axis, it precedes with some frequency omega 0, which is called also a Larmor frequency. So if we do some small estimations, that is, if we set the B equal to 1 Tesla, which is exactly in the regime where we want to operate, and set the G factor equal to 2, where happily enough, this value of 2 corresponds to the isolated electron, but also effectively it's close to what we observe in silicon. We observe that the splitting is of the order of 100 microelectronvolts. Then we can estimate the Larmor frequency, which is of the order of tens of gigahertz. And this is a very important, relevant information for us, because that means that we can operate, we can actually influence the spin in the microwave regime with pulses within the microwave regime. And this is already done, and this would be in fact the basis of single qubit operations. So let me then go to the architecture that is very important, because it was one of the first very concrete proposals for the spin quantum computation, but also this is something that we work on in QUOBLY. So Loss and DiVincenzo in late 90s, they proposed to use a single electron spin as a qubit. Is there some problem? Sorry.
I can hear you, Marta.
I can hear you as well, Marta.
Okay, sorry. It's just like I've seen lots of messages, so I don't know if it's on my side or.
It looks like some of them didn't. They lost the sound, but maybe it will come back for them.
Okay. So let me maybe continue. If this proceeds, we can then take a look again if there is some problem.
Yes, of course.
Thank you. So, what, as I was saying, the idea is to use a single electron spin as a qubit. Such spin is confined in an electrostatic or gate-defined semiconductor quantum dot. Okay. So let me first of all go through this very nice sketch of an actual device. So we use a semiconductor heterostructure to create a 2D electron gas. So this is this layer marked with black. Why we use semiconductors? Because we can really create layered structures. We can tune the electronic properties, so the band gaps, and in particular at the interfaces of these layers, we can trap the electrons from the 2D electron gas. So in these systems, electrons are trapped vertically in this very thin layer, which is often of the order of nanometers thick. And initially, the electrons in this layer can move freely in this horizontal plane. So to trap a single electron from this pool of many electrons, we have at the top metallic electrodes that are deposited at the top of the surface, for example, using like some lithography techniques. So when we apply a voltage, a very precise DC voltage in the range of millivolts to these gates, we in fact shape the electrostatic potential landscape of this 2D electron gas, which is below. So with this proper manipulation of the voltage, we are actually able to trap one electron and therefore one spin. So here in this plot, we have a dot, which is marked with a circle, the dotted circle, and then each of the electron holds a single electron spin, which is denoted here with this arrow. As I said before, just to have this canonical gap two-level system, we apply the magnetic field, the static magnetic field along the z-axis, and how we can now control the single qubits here. This can be done in two ways. There are pros and cons for both of them. So the first one is by applying alternating magnetic current in the XY plane, which is on resonance with the Zeeman splitting. This is something which is called electron spin resonance. Or there is another alternative way, which is based on oscillating electric field, which is created with these backgates, which effectively change the shape of the wave function of the electron. So this second option allows us for like full electric, all electric tuning of the system. However, for the time being and what we develop, I will focus on the first way of scaling that is based on varying magnetic field. So as I said before, we have this canonical two-level system. Here, as a small comment, this is really a convention, but sometimes it may be tricky, that despite the fact that we are saying that the zero state has a lower energy, it's still at the north pole of the Bloch sphere, so that's not a mistake. And just to say that for the rotations around x and y axis, that would correspond to rotating to shifting this state vector in these two directions. For this, we need active pulses. However, with the z pulses, for example, as we saw, because there is this natural precession, we can, for example, wait a little bit and effectively have a virtual rotation along the z-axis. So this is for the one qubit gate, but how we can realize the 2-qubit gates here. So the coupling between two neighboring spins, so for example this and this, is controlled by changing the voltage on the electrodes between these two dots. So that means that we are changing the voltage, and effectively the wave function of this and this electron starts to overlap, and effectively these two spins are interacting with the exchange coupling, which we call here J. So this is in fact a simplest way to see the Heisenberg interaction in the systems. Just we observe the overlap of the wave functions, and the strength of the coupling directly depends on the controlled voltage. And as I said, the readout is based on the spin to charge conversion. So we cannot measure the spin, a single spin directly. It's just too weak magnetic. But the trick is that what we can do is that we can push the electron that we want, for which we want to measure the spin, into a neighboring dot. So for example, this guy pushing this to this one. And if we know the spin of this neighboring dot, we actually can observe two situations. So if the two spins are opposite, they form a singlet, meaning that two electrons can occupy the very same dot. This comes from the Pauli exclusion principle. Therefore, we observe the charge moving. However, if the two spins are the same, they will form a triplet. And according to Pauli principle, it actually blocks them from sharing a dot. So the electron from this dot where we want to measure, it's staying aside. It doesn't move. So there is no charge movement. So a single electron transistor, SET, is actually able to really, it's very sensitive to this charge measurement, so that if the single charge is moving, it actually outputs like a microscopic current that we measure. And this way of encoding the computational basis is one of possible ways. I just want to briefly mention the other implementations to give some credit. So, for instance, in late 90s, Kane proposed a slightly different approach where we still use like a single spin states. However, we use the embed. So what we do is that we are having a silicon system to which we are embedding the phosphorus dopants. These dopants have a non-zero nuclear spin. So via hyperfine coupling, the nuclear spins interacts with the electrons, and this, for example, leads to very nice coherence times for the systems. Another one which uses two spin systems as a basis for the computational basis is that the logical qubits are encoded in this singlet or triplet states. So just to say, this is a nice thing because the way this computational basis is defined, we effectively are immune to global magnetic field fluctuations. So this level of complexity allows us to be immune to some types of coupling with environment. And finally, there is another class which requires free electrons in a triple dot, in fact. So then the computational basis is actually formed by the two degenerate states with a total spin 1/2. And what is interesting is that for these systems, the control is done only via the J coupling. So even for the single qubit rotations, we do not need any microwaves. So one may ask, okay, we have spins, we have spin qubits, but why actually the silicon spin qubits? So first of all is that we already observe excellent fidelities both for single qubits and 2 qubit gates. And these metrics are very recently also reproduced in a foundry environment. So we are not anymore in this academic setup, but really in the industry one. And like as a rule of thumb, if we have fidelities higher than 99%, we can actually think about realizing some quantum error correction codes and fault tolerance computing. The second thing, which comes directly from the physical properties of a silicon, is that it has rather weak spin-orbit coupling. So as a small comment, we know that spin-orbit coupling depends on the atomic number. It actually scales cubically with an atomic number. So that's why we observe stronger spin-orbit coupling in heavy elements. For instance, one of the first materials realizations for this Los Di Vincenzo qubits was in gallium arsenide systems. And these were having much stronger spin-orbit coupling, which is on the one hand side good because that allows for a faster control, but that also means that the system couples much easier with the environment. So any noise couples much easier. So if we have a weak spin-orbit coupling, we actually observe better spin lifetimes and coherence times. And in this paper from 2025, actually people reported very nice numbers for silicon spin qubit devices. So let me give you just the idea what it means. These 3 time scales are actually one of the ways to describe the performance of the qubits. So T1 corresponds to the energy relaxation. So let's say that we have a spin which is in the excited state, and then we are waiting how much time it will take for the spin to flip to the zero state. So this is an enormous time. It's almost 10 seconds. So for these, so seeing the other scales, it's really long time. And this, we know that this is suppressed by weak spin-orbit coupling because the spin and the lattice degree of freedoms, they do not talk to each other. Then we have a T2 star, which quantifies the phasing from all type of noise, both high and low frequency. And this time T2 which is actually measured in the Han echo experiment. This tells us about the lifetime when we are able to cancel the static part of the noise. So only when the fast part of the noise remains. So just to say, these numbers are really good, because if we think about the gates, how much time it takes to execute the gates, it's more of the order of tens of hundreds of nanoseconds. So we are much below this limiting times. And the third thing is that really the dot size, the sizes of these quantum dots are of the order of 50 or 100 nanometer scale, so really close to the transistor size. And therefore, we can really leverage the existing fabrication technologies and make the chips really dense, which is, for example, a great advantage in comparison to transmons, where a similar chip would take actually millimeter given the size of transmon. And finally, recently we observed lots of works were discussing a more complicated arrays, so the sets of quantum dots not only in the 1D as a chain, but really like full 2D structures. And this is very important for quantum error correction. We need this 2D connectivity with a grid to realize the quantum correction, like a surface code. And while creating an array of a 2D array of quantum dots, it's right now not that challenging, but wiring them, connecting these qubits is really difficult. And people have already come up with many interesting ideas, like some overlapping gate layers, which leads us to the second slide, is why maybe silicon can be challenging for some of the cases. The first problem that we observe in the systems is something which is called the valley splitting. So in order to understand why it happens, we need to go back to just bulk silicon. Bulk clean silicon has actually, if we look at the band structures of the silicon, it has a 6-fold degenerate conduction band, and this degeneracy comes from the crystal symmetries of the system, because it has actually a 6-fold rotational symmetry. So when we take a bulk silicon and we make out of it a heterostructure, we effectively lifting some of these degeneracies. So what happens is that out of 6 states, 4 of them are actually moving higher in energy, the other 2 are going low. So apart from having only spins in ideal situations, we right now have actually also the states with the valley, which are very close in the energies. So we can see that the ground state is in fact like a 4-level state manifold. And the problem lies that if the valley splitting is small, and these are the small numbers, we can observe some sort of a mixing between the states. So for example, we prepared our computational basis only for one valley, so spin down, spin up, valley 1, valley 1. But then if we have the valley splitting, so the separation between 2 different valley states, very small, what can happen is that if we want to perform a spin flip, we no longer stay in the same valley state, but actually we go to another one. That creates a leakage outside of the qubit states. We are not longer in our defined 2-level system as we wanted, and therefore we lose all the quantum information. Of course, there are some attempts how we can use the valley and spins together to create quantum computers. That's called valleytronics. But here, just for spin, it's really a problem to have these valley splittings such small. The second problem, it also is connected to how we create the devices, and it's the G factor variation. So as you saw, the very same G enters to the definition of the Zeeman splitting. So the way, so G factor can be used to have larger Zeeman splitting. But the problem lies in the fact that if we have a perfectly uniform crystal, then every qubit would have exactly the same Larmor frequency because the G factor would be a single number. However, in the heterostructures, we don't have such a nice case. Like there are actually, due to some strain, interface roughness, we see that there are some small modulations of qubits Larmor frequencies. And that makes, that poses a problem when we would like to address all the qubits with magnetic field, because yeah, like they actually have a different Larmor frequency. So we are not addressing them as we want. And this problem can be particularly visible for the large arrays where we have lots of qubits close by, which is also called the frequency crowding. The third point is related to the nuclear spin bath that we can have in the systems. So for classical electronics, for classical computation, we also use silicon-28. However, silicon naturally has several isotopes, and in particular, silicon-29 has a non-zero nucleus. So as it was mentioned before, if we have like nuclear spins and electrons, they can actually interact via like hyperfine interactions. And this effectively leads to the smaller values of T2 star, the coherence times. And this problem can be completely mitigated by the process which is called isotopic purification, where we are really forcing, like we really want to have only silicon-28 and completely, completely remove this the silicon-29 from our systems. So now imagine that we are very good at our laboratory, that we are able to make the perfect device, being sure that we control the valley splitting, the G factor, do the isotopic purification. And then there is always this problem, which is dominant actually. It's a dominant noise channel in these systems. So what happens that we have some electrical charges that are leading to detuning the electrostatic energy difference between dots. And that's because this detuning, we use this detuning to change the exchange coupling. So what happens is that just the presence of charges can, in an uncontrollable way, change the G coupling, and leading to really limit the existing gate fidelities. So this charge noise, it's 1/f, 1/frequency, and it has a very particular structure. Namely, it has a memory, it's correlated in time, and most of the spectral power is in the low frequency spectrum. So this kind of noise actually requires some work to be simulated correctly, because we most of the time work with Markovian noise, like a white noise, which is memoryless. So here, that was one of the motivations why we wanted to develop the SpinPulse code, just to really faithfully represent, simulate the noise present in these systems. So that points me to the second part of the talk. And first of all, let me acknowledge the people that have been working on this project for some time. It was really a collaboration between quantum information theory, quantum error correction people, software, hardware. So really, there were lots of backs and forth to be able to faithfully represent the noise and the simulations. And just to say, it's not the over. This project is still ongoing, but the main motivation was indeed to model the presence of realistic noise. So the standard gate level quantum simulators, they mostly focus on idealized cases, or when the noise is known in a sense that we can specify that, okay, this is a depolarizing channel and so on. However, they really fail to capture this reality of 1/f noise. So as 3 main points why SpinPulse may be interesting for you is that it models realistic time-correlated classical noise, so this charge noise that I tried to present briefly. The second thing is that it accounts for the physical shape of the microwave pulses that we used for the single qubit manipulation. So in the lab, of course, we cannot do things instantly. We cannot pulse the system right away. There is some duration, there is some width of the pulse. This is what we also implemented. And finally, the operations are actually optimized to native set, which is in silicon spin qubits architecture. So there are 2 ways how you can play with the code, how you can download it and install it. So it's a fully Python code, so you can either install it via pip in the virtual environment or directly download it from the GitHub. The version is open source, so if you have some more questions later on, you are more than welcome to see what's happening. There is also quite a lot of documentation, and my presentation is trying to take like the best of it to present to you. But if you feel like you want to learn more details, I also strongly recommend to go to archive and see this paper on SpinPulse. So let me briefly sketch the workflow, how the code works. It consists on 3 steps where, given an abstract circuit, we are performing the gate transpilation. So we are rewriting the circuit in terms of the gates that are native to the hardware. Or in other words, we construct the instruction set architecture circuit. And then each of these gates is being represented as a set of pulses. So for example, we have an Rx gate here with an angle pi. This corresponds to this pulse instruction here. Then, for example, we have the ZZ, so the 2-qubit gate. This corresponds to this pulse drawn here. So each gate is represented as a physical pulse. And then what we do is we perform time evolution separately per the pulse. And what we get at the end is the implemented circuit. So we get back the unitaries, which are corresponding to each gate. But right now, they can, for example, include the effect of the noise, because the workflow is very much similar whether we have noise or we are in the noiseless case. And as a small comment, the way the code implements the time evolution, so for example, these numbers that you have here, these are the sampling times is arbitrary in a sense that it's for the user to define what is the unit. So through this presentation and also for the notebook part, we are saying that the time is equal to 1 nanosecond. So each of the step is 1 nanosecond. All units are expressed in the terms of h bar, so you will not see the h bar in the definition of the Hamiltonian. And then the angular frequencies are in radians versus over selected sampling time. So just as maybe small comments, today I would like to fully avoid the discussion about exact parameterization. which would correspond to realistic QPUs. This is a separate ongoing project, and today I just really want to focus on the capabilities of the code per se. Okay, so let me go through the details of each of these steps that were on the graph. We start with the abstract circuit, which is a quantum circuit object from Qiskit. So that means that if you use some other libraries, you can actually rewrite it with some internal functions of Qiskit to be Qiskit compliant, and then you can provide it to SpinPulse. And we use the transpilation passes that are already available in Qiskit. So if we want to perform the single qubit gates, single qubit rotations, this is a definition of the rotation matrix. Here, sigma corresponds to the Pauli matrix, and the theta is the angle provided by the user. So in the code, we are not constrained to have only, for example, angles like pi or pi over 2. The user can take any angle he or she wants, and then it is inside of the code that the duration and the shape of the pulse will be changed so that the asked angle will be possible. So what is nice about the single qubit is that the Bloch sphere has a SU2 symmetry. So any rotation on the sphere can be achieved via something which we call the Euler decomposition. So it's actually rotation around z times around x and times around z, where alpha, beta, and gamma are just some angles. And this is a very nice decomposition, because we can take any arbitrary rotation and represent it as this product. And as I said before, for this hardware, only X and Y gates are truly physical, like the ones that are really requiring microwave pulses, which can be error prone, take some time. But the Z rotations are pretty special in the sense that you can think about them as a rotation of the frame of the reference of the qubit. So it's just enough to shift the software reference frame of your microwave generator, and then use this offset for any other rotations. So effectively, qubit sees a Z rotation without the physical pulse. So this is then instant and also immune to the error. And in order to realize this rotation angle, we actually integrate the drive field beta, B of I, which is I corresponds to the qubit index, over the given gate duration t. And as of today, we implemented two shapes for the pulses, Gaussian and square. And this allows us to compare the results, numerical results, with the analytical ones. And then we implemented the 2-qubit gate, RZZ, and then the rotation angle depends on the exchange interaction over the gate time duration. And just to say that this gate at pi over 2, up to some local Z rotations, is actually equivalent to the CZ gate, to controlled gates. So that means that with this implementation, we actually have a universal set of gates, and we can implement any algorithm here. The second step is related to going from the gates to the pulse, so the pulse level transpilation. If there is one thing that I would like to say as a take-home message in terms of the syntax for the SpinPulse, that would be the pulse circuit class, because it actually converts the circuit into the pulses. through three internal steps. So first of all, we are dividing the circuit so that each qubit has at most one gate per layer, and then all the sequences in a layer share the same duration. So this is, for example, what you can see here. This is layer 0. So we have these two pulses, two gates, two pulses sharing the same duration. Then per each layer, we are defining a list of 1 qubit and 2 qubit operations, because we know that 1 qubit and 2 qubit gates will be described slightly differently in terms of Hamiltonian. So then each of the sequence actually contains the time-ordered pulses, bare pulses, described by these Hamiltonians. And just to say, in this class, we have a set of instructions separate for the idle, for the delays, where the qubit does nothing. It just acquires like some phase, for example, due to the noise. And then a set of instructions specifically for active gates, for rotations, and maybe just to repeat myself, is that within this subclass we have a function from angle which actually adjusts amplitude and duration for a targeted theta, for the targeted angle that we want to rotate. So the single qubit instruction, the Hamiltonian for this instruction is written in the rotating frame at qubit frequency omega I, and looks like this. So here the B is a pulse envelope amplitude, and phi corresponds to the rotation axis. So for instance, if we want to realize the X gate, we can set phi equal to 0, then this term vanishes and we have just the X gate rotation. In a similar way, if we set phi to pi over 2, we realize the Y gate. The last term corresponds to the qubit of resonance due to the stock shift. So it's just that the qubit resonance frequency is a little bit different. And this is also separately per qubit, and it's not correlated with it, with other qubits. For the 2 qubit instructions, we use the Heisenberg exchange Hamiltonian. Effectively, we have XX, YY, ZZ, and then we also have the stock shifts corresponding to each of the qubits. This model does actually come from the existing literature, from the general formulation of spin qubits trapped in quantum dots. So I strongly recommend looking, for example, at this really great review to get a little bit on why we actually use these Hamiltonians. So we saw that the Heisenberg Hamiltonian contains both longitudinal and transverse terms, XX, YY, ZZ. However, when we want to do the RZZ gate, we are just interested in the ZZ term. So how can we go from the Heisenberg to the RZZ? So we can use the Schrieffer-Wolff transformation, which is a unitary transformation that allows us to separate the high energy and low energy spectrum of the system. So we can build an effective Hamiltonian that perfectly describes the low energy sector that we are interested in. So in this limit, that is when we are having large detuning between qubit frequencies, if we do some math, which is actually done in the paper, so for those who are interested, I strongly recommend to go there. What happens is that these terms XX and YY, they are actually averaging out in the rotating frame. So what we are getting from the Schrieffer-Wolff transformation is the effective Ising-ZZ interaction. However, by this construction, we still have a problem. That is, we have these terms. And so the start-shift terms do remain. And therefore, if we were leaving the gate as it is, such an RZZ gate would actually acquire lots of phase error coming from this single qubit terms. So the idea is to apply the X-pulse mid-gate, because this, what actually it gives is it cancels the errors on the single qubits. However, the ZZ term is immune to the echo. So effectively what happens is that having this Schrieffer-Wolff transformation and the refocusing X pulses gives us a robust RZZ gate. And the good thing is that this construction is done automatically within SpinPulse. So the RZZ that you use as the end user has all of these tricks implemented. The reason why I'm mentioning this is that in fact, if you, for example, compare the RZZ gate from SpinPulse and the gate from Qiskit, if you calculate the fidelity, you may have not exactly 1, but something very, very close to 1. And this comes from the fact that we are actually doing this small approximation. So the way we model the noise is by adding extra terms, either on single qubit Hamiltonian or two qubit one. So what happens is that we are just adding a classical phase noise. These are the random numbers drawn from some distribution, and they are also applied on Z. And for the 2-qubit noise, this noise is added on the J coupling. So we are adding like a small random factor, not only on the qubits, but also between them if there is a 2-qubit gate. So what is nice from the SpinPulse perspective, what can be called as a novelty, is that we really directly inject this noise. We are not using some depolarizing channel models. We are really doing like simulations, kind of Monte Carlo simulations, where we are generating random time traces multiple times, and then we are averaging over. So currently, SpinPulse has 3 different noise models. So how we are actually selecting the epsilon. So let me start actually from the middle, from the white noise. So this is a completely random noise in a sense that it's time independent, and for example can be used to model some thermal fluctuations, thermal noise. So each number is drawn from the normal distribution with 0 mean and the variance of sigma. And then what we can do is to do the quasi-static noise, which is non-Markovian. And it means that along some time, which we called a segment duration, this noise is static. So it's really constant at some time steps. And surprisingly, this is a very good approximation to what is happening for single qubit gates in the system. And finally, we have the pink noise, which here it's defined in a maybe a little bit convoluted way, but what we should know is just this is a function that generates this 1 over f noise profile, and this is depicted here. So what you can see is that it has some fluctuations, but there are also a slow drift. Like if you look, for example, a line here, there is a slow drift, almost linear at some steps. So for what we need here is actually, we need to have some low energy cutoff, because if we calculate the integral of this, we are landing up with the logarithm. So just to be able to calculate, we need some upper and lower limits, which are calculated internally in the code. But the point to say is that this drift, as you can see, like the reason why we need to have longer simulation to truly see the impact of pink noise, because the log term that appears from the integration here, it's a very slow function. So at the short times, the log terms looks almost constant. So the last step is the numerical gate integration. So if we remember from like a textbook, quantum mechanics, we know that the solution for the time-independent Schrödinger equation is pretty easy. However, here it's not the case. In particular, the problem that we have is that because both single qubit and two qubit Hamiltonians are time dependent, that means that at different times, the very same Hamiltonians, they do not commute with each other. So we cannot write like a closed form for them for the time evolution. So we have to do everything numerically. And how we do it in a SpinPulse is that we are, for each gate, for each time point, we calculate the time-ordered matrix exponentiation. So if we, for example, have a gate defined by the number k, we are really calculating for each of the time slice an exponent, and then we multiply it in a time-ordered fashion. So the complexity of such operation is t times d cube, where t is the gate time. But because we have two qubit, one qubit or two qubit gates, d is very small. So the cost is not that dramatic. And therefore, when we want to obtain the full circuit unitary, we are just calculating it as the ordered product of all pulse unitaries. So I want to clarify that this is exact. We are not doing any tritorization, these sort of things. It's really an exact time evolution. Okay, so now we can go to the use cases, which I hope you will find interesting. So the first one would be related to qubit spectroscopy, or defining one of the relevant timescales that I already mentioned, the T2 star. And this can be calculated, this can be determined via this experiment. So the protocol goes as follows. We are initializing our system. We are applying the Hadamard gate, and then we are waiting some time. And then, just to be sure that we can do the measurement in the Z basis, we are applying another Hadamard, and then we do the measure. So what happens here is that during the idle, it's only the noise that acts on the qubit. There is no any active gate. So any kind of a phase that is acquired by the qubit here, it really comes from the noise. So with this construction, we can actually cast this accumulated phase to a measurable population, the probabilities, and depending on the noise, whether it's pink or white, we will have a different decay shapes of the quantity that we call the Ramsey contrast. So because we are putting things because we are using the Hadamard at the very beginning, what happens is our state vector is on the equator of the Bloch sphere, just pointing at some other direction. So if we are measuring, we are actually getting a term which is the average of a multiple noise realization of cosine phi, exactly this phi that I was defining in for the Bloch sphere. So therefore, we can observe, we can repeat this experiment for different idle times. This is the T here. So for different idle times, we can plot the points and actually fit a curve and then read off the T2 star dependence. So, for example, for the quasi-static noise, what we see is that the decay is in fact Gaussian. For the white noise, however, this is really an exponential decay. And the pink noise has a way more complicated dependence, which is somewhere in between quasi-static and the white noise. But this really allows us to have like an experimental signature of the noise. Like these experiments are done straightforwardly in the labs. So a similar thing, a similar experiment can be run, which allows us to define this T2 coherence time. And as you can see, the protocols is pretty similar. We are again we are initializing some state. We use Hadamard. We are accumulating some phase. Then we are applying a single X pulse, which actually mirrors the phase sign. So if we accumulated something proportional to phi, here it changes the sign to minus phi. And then just to measure it in the basis, we are using another Hadamard. And what this does is that it allows us to define the T2 scale. And this is what we say, it's insensitive to the inhomogeneous broadening, meaning the low frequency part of the noise does not affect this T2. So that's why we have the ordering of the values in this way, that T2 star is almost always smaller or equal, in fact, to T2. So the Han-Echo experiment can be used for measuring this T2, but also we can see that just by applying the single pulse, we are actually cutting the effect of the low frequency noise. So this can be actually very important when we are dealing with the pink noise, which by definition has this 1/f spectral profile. So this technique, applying some sort of pulses to correct for the errors, it's called the dynamical decoupling. And in SpinPulse, there are two implementations of this. One is really spin echo, where we have just one X pulse, and this is very effective for quasi-static slow noise, but not very much effective for the white fast noise. And then there is some other thing that we implemented that is called full drive, which you can understand that is a continuous driving of the qubit during the idle period. So it's designed in a way that we would like to minimize the idle windows against the noise. The second use case is related to quantum gate channels. So normally the quantum gate channel is calculated as this average over multiple noise realizations. And this is interesting because, as I said before, we are really doing these Monte Carlo simulations with repeated trajectories. So we can model the quantum channel without actually using like Lindbladians, which the fixed Lindblads actually assume that the noise is Markovian, which, as we saw, it's not the case. So, one thing is that for each of the noise realization, we calculate the exact U per trajectory. So this is U corresponding to the full circuit. And then we calculate the ensemble average. One of the quantitative of interest is the kinematrix of a channel. So it's used pretty often in the process tomography. And basically, it maps the errors in a way that let's say that we would like to see the channels, the error channels of the X gate, okay? So what we would expect is that for an ideal poly gate, as we said, maybe let's take X, there will be a single peak at a diagonal element corresponding to chi XX. If there is a presence of some noise, the other diagonal elements will have some non-zero values. This would correspond to the weights of poly error channels, and the off-diagonal elements would correspond to the non-poly error channels. With this, we can also define the average process fidelity with respect to a clean, noiseless circuit, which is then defined as a trace over this product and calculate the square of it. Here, the D corresponds to the dimension of the matrix. So for the one single qubit gates, D is equal to 2. So with this, one of the added value of SpinPulse is that let's say that you design some pulse sequences outside of SpinPulse, but you, for example, want to test it if this pulse sequence will be robust in the presence of realistic noise. Then you can do the simulation with SpinPulse, or you can just really try to optimize your pulse just by testing some parameters within SpinPulse. So that would be very important for any future QPU modeling. We have also another very interesting example, because this is one of the algorithms which is supposed to show a quantum advantage. And the idea is, one can think about this algorithm as a restricted version of the Deutsch-Josa algorithm, where, just as a reminder, the idea was to distinguish between two different classes of functions, balanced versus constant. Here, we would like to learn a string, which is encoded in a function in an oracle. It's our black box function, which is defined like that. So this is a bitwise dot product. And our idea is to find S using the absolute minimum number of queries. So X is our input, is a bit string of a length of n. And if we think about classical strategy, for example, if n is equal to 3, we would probably think about querying this oracle by using the basis states. So the 1, 0, 0, 0, 1, 0, and 0, 0, 1. So with this, each query reveals exactly one bit of this string S. That means that classically, the best strategy would be to execute n queries. However, with quantum computer, that would be only one query, regardless whether we have a bit string of 3 bits or 3000. So just to say quickly how this algorithm works is that we have n qubits and one ancilla qubit, which is initialized in the one state. This set of Hadamards applied to all the states are actually creating a superposition of all 2 to the power n possible inputs. And then this target qubit becomes in a specific state, the minus state. And when we go further with the circle, what Oracle does is that because these qubits are in the superposition, the Oracle processes everything at once, and the results of this black box function is actually kicked back into the phase which each of these qubit acquires. It's either -1 or 1. The kickback is not my definition. It's really an effect which is called phase kickback. And the idea is that if you do again the Hadamards, there will be some constructive interference and destructive interference. So effectively, the incorrect bit combinations will be destructively interfering, giving the good answer that is the one which corresponds to this hidden string. And for the SpinPulse, why this algorithm is interesting is that it's really a stress test for 2-qubit gate fidelities, because as I said, the oracle is kind of a black box, but to really implement it in a circuit, we want to have the logic of this algorithm. We want to use some controlled gates, such as CNOT gate, to really execute this algorithm. And as we saw, because the RZZ is equivalent to the controlled gates, therefore this can test how the noise on RZZ affects the results of this algorithm. The fourth use case would be the randomized benchmarking, where we would like to estimate the performance of the gates, but really isolated from the state preparation and measurement errors. So these are called the spam errors. Why? Because we saw that the gate fidelities right now are very high, over 99%. But the reload fidelities are a little bit lower. So if we were to include the spam errors, actually such a direct measurement would hide the true gate error, because it's larger than what we have on the gates. So the randomized benchmarking consists of like 4 steps. The idea is to use the so-called Clifford gates. These are it's a very nice group mathematically, because it's first of all we can simulate it classically on the computer. So for the second step, for the recovery, we can actually instantly calculate the exact inverse for sequences regardless of any length, for any m. Therefore, what we would expect from such an algorithm is that if we have no noise, like the decay will be much lower, like the value of the fitting parameter would be much different than if we have the presence of noise. A small caveat is that randomized benchmarking was constructed for the Markovian noise, meaning that we are assuming that the errors per gate are completely independent, which is not the case for the noise with the memory. So this I'm just saying for you if you are interested to explore. And finally, the last use case is the combination of SpinPulse with some other external libraries. For example, with QuIMP for larger scale tensor network simulations. So as we discussed at the beginning, when we have a vector state, it actually scales exponentially with the number of qubits. So for more or less 15 qubits, what we see is that we just don't have enough memory to keep such a state vector on the computer. However, what we can do is that we can use the matrix product state representation, which effectively factorizes our vector state into a product of smaller tensors. So each of these tensor corresponds to a single qubit. It's a 1D chain. And the one parameter that controls, which is very important here, is the bond dimension, because this bond dimension controls the approximation error that we do with this approximate representation. So what is nice is that instead of having a vector which scales exponentially, we have something which has much better scaling. And as I said, we have some sort of a change that we are not longer limited in this simulations by the number of qubits, but more by the amount of entanglement we have in the system. So MPS works very well when we have low entanglement. Then we actually don't need to have such high bond dimensions. And this casting into this representation, which can be then used in another library called QuIMP, can be done directly from the pulse circuit object using Qiskit to QuIMP function. And in a couple of minutes, I will show a benchmark for one particular type of states, which are called 1D cluster states. So these are this is a very interesting class of states because they can be represented as undirected graphs, and all the entanglement is actually on the edges between the vertices, where vertices are corresponding to the qubits. And just to sum up this part, I believe that the SpinPulse provides a really nice framework for noise-accurate simulations at larger scales because it really brings this pulse-level realism, also hardware-native co-design. So we really work now to improve it even more, to optimize this native gate set. And it's very open for other integrations, so you can use it with your other codes for simulation. And just as a small advertisement, we expect that later in 2026, we will actually release the second version of the SpinPulse, when in particular we will address some performance issues, performance improvements, better time evolution, and also extension of the native gate set with better transpilation passes. So that would be this for the end for this part. Now I will look into the chat if you have some questions. I don't see things, if there was something direct. So I suggest that will be maybe a good moment just to have like a 5 minutes break. So it's 3:38, so maybe we can reconnect like, let's say 42, let's say. Thank you. I hope I can see all of you back, at least with a cup of coffee. Let me briefly go through this notebook. I'm not exactly sure if we have time for everything in details, but I would like to just briefly flash the capabilities of the code, like how does it work in action. So basically for this demonstration, I already prepared the virtual environment. You can use either UV or Conda, anything you want. And yeah, like the basic workflow is specified, in fact, here. Here I have some couple of imports, not that important. And the basic workflow can be shown here. So as I was saying during the presentation, we would like to do these 3 steps, and we want to do that on a simple CNOT circuit. Of course, you can say, why 3 qubits if for CNOT you need 2? This will come. So we need to specify a couple of parameters. B field, it actually corresponds to the maximal value of the magnetic field, so Bi in the equations. And then the delta corresponds to the detuning between 2 qubits, the maximal detuning. Then we have the J coupling, and then we have this parameter, which I call here a coefficient duration. Depending on whether we use the square pulse or the Gaussian pulse, this can have a slightly different meaning. So if we highlight one of the classes, this class is called hardware specs and is meant to define the hardware specification, as the name suggested. So if we have a square pulse, then this coef duration will actually go here. And this is how we can construct the hardware specs object. And all of this is documented inside the SpinPulse. The only one extra thing that we are allowing is the optimization flag coming from Qiskit directly, because this controls how the circuit will be transpiled. So of course we have also like a helper function defined for this class. So if you want to, for example, see how UR initializes the class, you can just do the print on it. So this part is just the Qiskit. We are creating a circuit. We are using, first of all, a Hadamard gate just to make things more interesting, because without that, we will always have zeros and ones. And this is how the circuit looks like. So now what we want to do is we are using the method called gate transpile on this very Qiskit circuit. This is how it looks. So coming from Hadamard and C0, we have just the set of rotations, Ry, Rx, Rz, and the RZZ terms. First of all, we want to be sure that the transpiled circuit is exactly the same what we defined originally. Okay, the fidelity is equal 1, they are the same. And now we would like to plot the pulses, like how this circuit looks in terms of pulses. So we have this one qubit which is empty because we are doing nothing on it. But then for the rest, for the two, we actually have single qubit gates, Ry, Rx, and also Rz. And for the 2 qubit, we have this extra panel here, corresponds to the Heisenberg interaction. So how we can integrate? We are using the function toCircuit on the pulse circuit, and this leads us to this integrated circuit, for which we can either use like a function average gate fidelity, which comes from Qiskit, or we can use the function that is implemented in the SpinPulse. The good thing is both of them are giving the same answer. Really, it's the very same implementation, in fact. Okay, that was just to show the basics. What happens when we add the noise? So in order to set up the noise, we are using the experimental environment class from SpinPulse. It takes the hardware specs. We specify the noise type. So we have 3 possible options. Here we define the coherence time T2 star. So the higher number, the more resilient the qubits is. And here we have these 2 parameters that I briefly mentioned. Duration corresponds to the total duration of the circuit. And then the segment specifies the duration for the noise generation. So, for example, when we want to generate only the white noise, this would go to 1 because it's just generated at each time point separately. Okay, so we can use the very same pulse circuit from circuit function, but now we are actually adding this term. So we are adding the experimental environment to the from circuit method. Okay, when we plot, what happens is that we have right now these black lines, which are actually a little bit wiggly. And this is because there is a noise. So these are really the time traces that we. And finally, what we can do is to calculate the average fidelity over the noise realizations. So it's not like I am just plotting one time trace and calculate the fidelity. It's really an averaged value over multiple noise realizations. So what we see then is that if we have the pink noise, the fidelity drops to 0.9 as expected. And if we were, for example, changing this guy to something smaller, which, okay, I didn't, okay, I see why. I would have to run everything again for this case, because I ran the full circuit, but we can go through the other examples. Sorry for that. So what we can do is we can look how this dynamical decoupling technique allows us to improve the fidelity, the average fidelity. So how does it work? Is that as I mentioned, we have implemented two dynamical decoupling strategies, full drive and spin echo. And in order to use it, we just create another instance of hardware specs, now with this dynamical decoupling variable, which we set to full drive or spin echo. The same story goes. We calculate we use the method from circuit right now with these new hardware specifications, and then we can compare the fidelities with and without dynamical decoupling. So as expected, with dynamical decoupling, we have a higher fidelity, and this full drive is actually the best one because, as I mentioned, it both fights with low frequency and high frequency noise. And now what you saw before here was nothing, right? The qubit was idle. It was this one qubit that was not participating in the synod gate. And now with the drive, we see that indeed there is a dynamical decoupling applied to this idle qubit. The Ramsey and spin echo experiments, we can use some functions which are already defined. Again, having a setup for a single qubit, because this is how the protocol works like. And then with the get Ramsey circuit, we are specifying the duration, the idle time, and we can also use the internal function get average Ramsey contrast, which calculates this Ramsey contrast as a function of the idle time, and we get like a curve with some of the with a decay. So we can, for example, play a little bit with different noise types, noise strengths to see how this curve differs. For the spin echo, we do essentially the same. And in particular, here we can compare the two different dynamical decoupling schemes, seeing really that the full drive is the best in a sense that it has the highest contrast at the end, followed then by spin echo, and without dynamical decoupling, we see the decay. For the average super operators, here I just want to show how the graphical representation of the chi matrix looks like. So if we have an idle qubit, so it just has this delay, it's a very simple circuit. We see that because it's idle, so the highest weight is on II. However, there is some small contribution on ZZ, which comes from the presence of the noise. And we can compare this with some analytical solutions, which are very nicely discussed in the paper. And if we have an active gate, for example, a single qubit X gate, now we see that the weight comes to XX as expected, but still there are some contributions just coming from the noise. And again, we did some nice analytical solutions, which we can also plot and compare with numerics. The same we can do for the 2-qubit RZZ gate. And as I was mentioning, for 2-qubit gate, we can also add the noise on the couplings, not only on qubits per se, but also on the couplings. And this is done a little bit lower, is that with experimental environment, if we set some value here, then similar to specifying T2 star, we have TJ star, which tells us about, this effectively adds the time traces to the couplings. Okay, so again, we can compare numerical fidelities with analytical solutions, see if it really works. And for the algorithm, I will also just briefly sketch that we can construct an appropriate circuit. Here we are just constructing a couple of hardware specifications just to compare the effect of the dynamical decoupling and without it. And this is how the oracle looks like in case of 3 qubits decomposed into the native gate set. And if we run the experiments, we can actually plot a histogram. And then we see that, for example, we ask for the string 011. This first one comes from the fact that we have an ancilla at 1. But what you can see is that with dynamical decoupling, we get a higher probability for the correct answer. So this way we can also study how it changes depending on the noise type, noise strength without dynamical decoupling. And for the randomized benchmarking, so here we are using just a function to construct a circuit of a given length m. Just as a small comment, the number of Clifford gates does not necessarily correspond to the number of the native gates because they need to be decomposed. So that's why, despite me selecting 5, we have more than this because we have some of the gates are decomposed, and then we have to do the inversion. So what we implement here is the calculating the survival probability, and we can actually plot it, for example, for multiple m values at realized several times. I think for this example I selected 100. We can plot the data time points, and then using SciPy just find a curve that would match this. So it's actually pretty nice to explore like whether really this decay, this exponential decay, is a good approximation for the non-Markovian noise or not. And finally, like this I put actually as the experimental part, because this is something that we even want to work a little bit more, is to look at this interface of SpinPulse with QuIMP. So I am defining this one, the cluster state, and also just to calculate the fidelities in QuIMP, I calculate the ideal state with no noise. And here I can actually go to larger number of qubits. I selected 25, we can easily go to 100 on a personal computer. And then actually the circuit, it has a straightforward structure, but there are lots of gates for 25 qubits. And again, we are doing the very same thing. We have a pulse circuit object. We call the method to circuit. And then this actually contains the list of unitaries that are then passed to QuIMP directly. So for example, I'm selecting 0. This corresponds to this guy. And then given the way it's indexed, 25 would be actually this guy. And yeah, like we can look a little bit into the scaling, meaning that for the pink noise, we can, or for any other thing, we can just write a simple loop across number of qubits and the number and different T2 stars, calculate the fidelities, also averaging over multiple samples, so we have the good statistics, and then plot this for example, represented here. And what it tells us is that indeed we see that the fidelity scales like that with the number of qubits over T2 star squared. So I think I'm perfectly on time. With this, if you have some questions in the last minutes, please feel free to ask. And if something comes to your mind that you would like to learn more, or I explain something maybe not completely, feel free to contact me either via email, on LinkedIn. I'm pretty sure, if not me, I will be able to find a contact with someone from the company that can answer your questions. Thank you.
Thank you, Marta. Thank you very much. If you have any question for her, please use the chat. Now I only see clapping hands for you.
These are the very good questions. Thank you very much.
Okay, it looks like there's no question. You answered everything during your talk. Congratulations. But as Marta said, if you have any question later, you can of course, contact her or contact us, and we'll follow her the questions. We will end this session now. Please note that there will be the replay available soon on the YouTube channel, and also we'll have the next session next week with Alain Champenois. Maybe, Alain, do you want to say a few words before wrapping up?
In fact, next week we are going to talk about quantum algorithm and specifically the paradigm of quantum computing reservoir paradigm. And we will also, at the end of the presentation, use some results with SpinPulse that has been presented today. And that's it. So I'm looking forward to exchange with you about that.
Okay, so you'll have the link in the chat if you want to register, if it's not already done. Thank you very much, everyone, for today. Thank you a lot, Marta. This was great to have this webinar with you today, and I hope we'll be able to do other ones together very soon. And see you next week.
Thank you
next week.
Goodbye,
Thank you,
everyone.
everyone.
Bye.
Bye.